There's supposed to be some kind of warning popping up.
It popped up for me.
Oh, it popped up? Okay.
Yeah.
All right, good. So I guess then we can slowly start. So it's a great pleasure today to have Matteo with us. Matteo did his PhD at Princeton, which is where I first met him. And, then he went on to do lots of interesting things in quantum dynamics. And he's currently at Stanford and, well, soon moving to greener pastures, as they say, in Texas. Matteo, please go ahead.
Great. Yeah, thank you so much, Zlatko. Thank you for inviting me. It's a great pleasure to speak in this very interesting seminar series. I'm going to talk about some recent work that we posted at this reference here on classical shadows, which I will review, and how you can use insights from quantum dynamics to understand them better and potentially improve their performance. And this is work that was done with Yao Dong and Tibor, who are also postdocs at Stanford, and Vedika Kemani. And please feel free to interrupt at any point if anything isn't clear. And Okay. So yeah, generally speaking, the motivation for this work is probably the same as many talks in this series, which is that we have now these quantum technologies that are really pushing the boundaries of the kinds of things that you can do with engineered quantum systems. And in particular, they're allowing you to make use of almost all of the ingredients of quantum mechanics in a really novel way. And this allows you to prepare quantum states that are increasingly complex and entangled, as opposed to maybe simple ground states that you might prepare in sort of more traditional condensed matter systems. And this is, of course, very interesting from a fundamental physics perspective, but it's also a bit challenging. On the one hand, for theorists and for classical computation, you might have certainly have seen the random circuit sampling experiment by Google, for example, whose whole point was that you're preparing a quantum state that is inherently difficult to describe classically. And so that kind of pushes, challenges the boundaries of classical simulations. On the other hand, preparing these kinds of complex states is also challenging for experimentalists. So not just for making these states, but for convincing yourself of having made them, for example, of being able to diagnose a certain property of a state that might not be as obvious as some local expectation value. Okay. For example, you might want to measure entropy, which isn't as obviously measurable as more sort of common linear operators, or fidelities or quantities that don't have an obvious experimental counterpart. And so this kind of motivates the search for efficient experimental tools for really characterizing general quantum states. So in complete generality, the way that you would go about this is to do a full quantum state tomography. So given many-body quantum state is some big, some exponentially big density matrix, you could, in principle, by making some exponentially big number of measurements, characterize every single entry in the density matrix, and then you would know everything there is to know about the state. However, of course, this is exponentially costly. So this is clear if you're literally going about this entry by entry, but you might think maybe I can do something more clever and get around this. That's not the case. So there's been work on fundamental sort of complexity theory of this problem, and the optimal thing you can do, even given access to quantum memory and doing entangling measurements between many copies and so on, is still exponentially costly. So 4 to the n scaling in the number of qubits. So this is not experimentally viable beyond sort of few body systems. I think the record might be around 10 qubits or something, around that value, but certainly you can't go much further than that. And so, again, if we want a complete description of a state, there is really nothing better we can do, and we seem to be stuck. The idea is to, what if we give something up and, accept that we're not going to have a complete description? In that case, can we do something that is efficient and useful for many things? So to be specific, can we learn a compressed description of some sort of our unknown quantum state in a way that is efficient quantumly? So it requires a number of preparations of the state that is, not unreasonable, and also efficient classically, so that any kind of classical post-processing I need to do can be done in polynomial runtime on a computer, a classical computer. So this is the general question that classical shadows set out to answer. And just to give you a very first introduction to this, the idea is to learn many properties of a quantum state from a relatively low number of experimental realizations by making use of randomized measurements. And I'll say what that means in detail in a little bit. But for now, what we mean is that there is a state that we don't know. We go in and we apply some random unitary that has to be specified. The ensemble has to be specified. And then we measure, collect some data, and run it through some classical post-processing step. And by doing so, we build some kind of compressed description of this higher dimensional object rho into kind of projected onto lower dimensional spaces that we can efficiently store and use. So in particular, this description can then be used to answer many other questions about rho that you didn't necessarily directly measure during the experiment. Okay. And the name shadows comes from some prior work by Scott Aronson, my future colleague at UT, who was working on a more kind of theoretical computer science problem called shadow tomography, which is not the same thing. But anyway, the spirit is the same, and that's why the name is common. And the idea is that we aim to learn not the full density matrix of rho, but only the shadow that it casts on the measurements. So this is what is being sketched here. There is a higher dimensional object. It kind of casts a shadow on these measurements we performed that are kind of like hyperplanes in the Hilbert space, and we get a snapshot on those planes. And then by gluing them together in a suitable way, we can use this description to predict new things. So to give you a bit of a flavor of what kinds of things you can learn expectation values of observables. So the traditional things you care about in condensed matter physics. You can learn local expectation values, few point functions, and so on and so forth. You can also learn fidelities with many body states, which are, of course, a special case of an expectation value, but a very peculiar one. Kind of a non-local but low-rank operator can be learned in certain protocols. But also you can learn nonlinear functions of rho, which is very useful because those don't have a direct cannot be measured from a single shot of rho because any such thing would be linear in rho. Okay, so things like a purity trace of rho squared, but also more complicated entanglement functionals can also be learned. And what's very interesting is that you don't need to decide in advance what kind of thing you want to know. You can just run this protocol, build your description, and then later on go back to it and ask new questions. So to be really concrete, there was an experiment by the Innsbruck group in 2019 where on a trapped ion simulator, they aimed to measure entanglement of subsystems. And note that this was before classical shadows, so 2019 versus 2020. However, they made use of a randomized measurement protocol that happens to be one of the possibilities that you can use for shadows. And so that same data set could then be reused to learn other things about that same experiment. So for example, in years following, the same group and other groups have used that data set to effectively measure different quantities like fidelities, entanglement negativity, or symmetry result entanglement. So this is very promising and interesting in the sense that these experiments are difficult and expensive. And so this is a way of trying to extract as much mileage as you can from a fixed number of experimental realizations. However, the reason that, somebody on the physics side, such as myself, might care about this is that this protocol, involves a lot of the ingredients that have recently become very interesting from the point of view of dynamics, such as random circuits, measurements, entanglement in a many-body system, and the statistics of higher moment quantities that might have, if I have time, I'll say more later. But anyway, all of these ingredients that many people have been thinking about recently for a range of other reasons all come together into this protocol. And this suggests the possibility of interesting insights that can be gained from dynamics. And this talk is going to be precisely one such example. So in particular, to give you, don't be intimidated by all the figures and words. I will unpack all of that later. But in a nutshell, what we are going to talk about is a result that connects the efficiency of a particular version of classical shadows to properties of operator dynamics in random circuits, or more generally chaotic dynamics. And in particular, we highlight the role of a competition between two things that happen in two operators in chaotic dynamics. One of them is the well-known phenomenon of operator spreading that is at the heart of quantum chaos. The other is a somewhat lesser known or less well-studied manifestation of the same thing, which is operator relaxation that I will define. And with these insights, we find we characterize the optimal depth and optimal performance of a family of protocols, and we do so with an upper bound and with some kind of approximate analytical and numerical results. Okay, so before I get to the new stuff, let me give a review and an introduction to classical shadows, and I'll try to make this clear to a physicist. But if something isn't clear, please do interrupt me and ask questions. Okay, so the idea is, as I was mentioning earlier, is to take our unknown quantum state, rotate it with a unitary drawn from some ensemble that has to be specified, and I'm going to call it the twirling ensemble, and then perform measurements in the computational basis, which returns a bit string state, so a computational basis state indexed by a bunch of zeros and ones. And from this data, so the data on the choice of U from our distribution and the outcome of B, we can build sort of our best educated guess about the quantum state rho. And given only this data, the best we can do is to conjecture that our quantum state was the bit string we got rotated backwards into the original basis. In other words, we have gone in and we have rotated rho. We've found it to be in a certain basis state, and the best we can guess is that we simply rotate the state back to the original basis, and this is what this snapshot represents. Okay. Now, this is in and of itself a very poor guess for the quantum state, because even though you're applying some potentially big unitary, this is still a rank 1 projector. Okay, so rho was a generic quantum state which could be a full rank matrix, and this is a rank 1 projector, so this is not going to be close to rho in any reasonable sense, except it's going to have some little bit of information about it, some information which we can aggregate over different realizations of the protocol. And by doing that, if we average over many such individual snapshots, different choices of U and different outcomes of B, we find something that is as written here, it's just a weighted average of these snapshots by the probability of getting, the given outcome. This thing here is, as you can see, linear in the state rho. And it turns out to be a quantum channel. You can convince yourself that this is something like, measure and prepare. So it's like it's a well-behaved, completely positive trace preserving map, M of rho. Okay. So you should think of this as noise. It's basically a process that corrupts some of the information in rho, as expected. We are doing something, we're not getting sort of the exact density matrix. I'm doing this, we're getting some kind of corrupted version of it, and this is what makes it compressible into a classical computer. However, bear in mind that everything that's happened after this point is happening on a classical computer. It's happening in classical post-processing. It's not really a physical process anymore. And so it makes sense to ask whether this linear map, even though it's irreversible physically, whether it has an inverse, just as a linear map. And its condition is called tomographic completeness of the ensemble. And informally, you can think of it as whenever the ensemble is random enough, in some sense, then this map is going to have an inverse. If your ensemble were, for example, just z-basis measurements, then you could quite easily see that this resulting map would kill any off-diagonal matrix elements, and so it would not be invertible. It would have a singular inverse. But as long as you're doing something sufficiently generic, this is going to have this mathematical inverse. Okay. So the idea is let's take these snapshots and run them, again, in classical post-processing through this inverted channel. Okay. And doing this forms these objects that I'm going to call the inverted snapshots, rho hat, that are essentially the classical shadows of rho. Okay. In particular, it's important to note here that both steps, so both the multiplication of the basis state by U and the action of this inverse channel happen in classical post-processing, and therefore must be efficiently computable. We can't have, for example, U be a completely dense random matrix, because that would not be, we couldn't store this on a computer. We couldn't act on it with it on a state. So there has to be some care used in choosing these things. But I'll give you a couple of examples where this is very easily doable. And these inverted snapshots have the nice property of kind of by construction, by the way we've built them, to be to essentially return row in expectation. So if I take an average of these guys, again, I've defined them as M inverse of my snapshot sigma. M is a constant matrix, so I can take my average inside, and from the definition of rho hat from the definition of M as the average of these snapshots, I find immediately that I get a composition of M and its inverse, which cancels out. So in all, I find that the average of these inverted snapshots is my state of interest. So this is where the tomography aspect of this comes from. However, what I really want to avoid is having to actually build these, actually having to aggregate these inverted snapshots into forming an explicit description of rho. That's exactly what I don't want to do, because it's going to be exponentially big and I won't be able to use it for anything. So I want to find a way of answering questions about rho directly from my inverted snapshots without having to throw them all together and average. And to give an example of how to do this, we can compute an expectation value of some operator O. So the idea to do so is to build these estimators O hat, which are simply trace of O with our inverted snapshot rho hat, which is a random variable. So these in turn are going to be random variables valued in real numbers. And by construction, their expectation is going to be the correct thing we want. It's going to be the quantum expectation value of O. So this protocol works. In principle, if you collect enough of these shots, we process them, we compute these estimators, and we throw them together k times an average. This is going to give us the right thing eventually for sufficiently large k. But the question is, how efficient is this? And in particular, how many shots, how big does k need to be for me to get an answer that is within some tolerance epsilon? So if I want to get my expectation value plus or minus epsilon, the number of shots k I need is going to scale in this manner, just from computing the standard error of the mean from a population of random variables. I get this 1 over square root of number of samples that comes in, and if I want to bring this overall uncertainty to within epsilon, this is the number of shots I need. And so the variance of these estimators, little O hat, it's got two pieces. It's got the expectation of O squared and the square of the mean. The second piece is easy because it's just the square of this guy. And this is an order 1 number. If O is, let's say, a Pauli operator with bounded spectrum, this is a small number which I can throw away. However, this quantity turns out can get very large. Okay, so the whole game is to understand and quantify the scaling of these variances to see, what is the sample complexity of this protocol. That is to say, how many times do I need to run it to learn anything useful? And in particular, it turns out that this quantity here, which as you can see is quadratic in the operator O. So if you go back to the definition, there will be 2 copies of O coming into this quantity. Turns out this behaves like a squared norm. It's like an inner product of O with itself according to some particular inner product matrix. So this defines a norm that is known as the shadow norm. And this crucially depends on how you choose the random matrix ensemble to go in here, how you randomize your measurements. And so the whole kind of question about the applicability of this protocol is, how does the shadow norm scale for different operators given different choices of this randomization process? So to give 2 concrete examples from the original paper by Huang, Kung, and Preskel, we can have the simplest protocol, which is essentially applying local random matrices. So you go in on each qubit and you apply a single qubit Haar or Clifford random unitary. And then you run through the protocol that I discussed just now. So if you do this, it turns out that the shadow norm of a Pauli operator O that acts on k sites is going to scale as 3 to the k. So this is, of course, going to be prohibitive for extremely high weight Pauli operators that are supported on the entire system. But as long as you care about local expectation values or few point correlation functions, this is going to be scalable. In particular, it doesn't care really about the number of qubits in the system. You could have a thermodynamically big quantum state, and you would still be able to efficiently measure 2 or 3 or 4 point functions on it, which is useful. And it's also very easy to implement on quantum hardware because these are essentially unit depth quantum circuits, and noise is not going to be terribly harmful. On the opposite extreme, we have global twirling, where we go in with an n-qubit random matrix. And here, for considerations of classical efficiency, we have to choose a Clifford operation, which is going to be efficiently simulable on our classical computer. And if we do this and we run through the protocol, we find that the shadow norm reduces to the Frobenius norm, so a trace of O dagger O. Now, this is going to be prohibitive for any Pauli matrix, no matter locality. Of course, locality doesn't matter because we just randomized everything in a many-body way, so locality is lost, and so this is unsurprising. But in any case, you see that this scaling as 2 to the n with the number of qubits is going to make this not viable for learning this kind of expectation value. What this is good for is, for example, a many-body fidelity. So, if your operator were a rank 1 projector, then the thing you're learning really is the sandwich of rho between psi, and that's the fidelity, which is often useful, for example, to figure out whether the state you've prepared is really what you thought it was going to be. However, this is also, this can be hard to implement on noisy quantum hardware because you don't have at your disposal a big random matrix. You have to factor it into a circuit, a deep circuit, and the noise is going to be very severe. So there is an interest in trying to bridge these two extremes and find intermediate protocols that have some of the benefits of both. And this was proposed just in the last few months by Yizhuang Yu's group at San Diego and Jens Heisert's group. And the idea is to employ random circuits of finite depth to do this randomization. So this is, of course, motivated by, again, kind of NISQ considerations in the sense that shallow circuits are, going to be less prone to noise as opposed to deep circuits. There is also a consideration of classical complexity of handling these objects. So specifically, I'm going to use T to indicate the depth of the circuit we're looking at. And I'm always going to implicitly assume that there is a random single qubit operation at the start and at the end of this step. So right before the circuit and right before the measurement. The stuff in between could also be non-random. I don't strictly require it to be a random circuit, so that's the practically easiest thing to look at. And so let me also highlight that this state rho is going to presumably come from some kind of dynamics that happened before. I am never going to be worrying about that. Rho is just given, and every time I mention time, I'm really talking about this randomization. Okay, so when I have O of t, that always means like some time evolution that has taken place during this randomization. Okay, so here essentially the classical post-processing becomes a little bit more complicated as opposed to the two cases that I just mentioned, where it's straightforward. In this case, you have to use tensor network methods to handle the shallow circuit, and this poses a constraint on depth because the classical computational time scales exponentially in t. So as long as t is sublogarithmic, with number of qubits, we are okay. This is going to be polynomially doable on a computer. And in terms of performance, this was found in these two papers to be really quite powerful for reasons that weren't clear at the time. And you can see that as a function of this circuit depth that you're using, the shadow norm of a Pauli operator that acts non-trivially on k sides in a row in one dimension. We're always going to be thinking about that kind of operator. So like a Pauli string of some length with no identities in the middle, just traces Paulis all the way. For such an operator, the shadow norm starts out at its 3 to the k value, that is the local twirling value, and then very quickly drops exponentially by orders of magnitude to some lower value, at which point it starts to diverge exponentially in time again. And in between, there's going to be an optimum of the shadow norm at some finite time, which you can try to extract, and it has a roughly logarithmic scaling. But of course, this fit is not as good as we would like it to be because of the discreteness, essentially, of time. So you only have a handful of steps to fit, and the accuracy isn't as good. So the question that kind of got us thinking about this is, why does this behavior arise? This is quite surprising. You might have expected that the optimal depth might be linear in K, for example, by on grounds of causality. You might think you need to fit some light cone in there, or something like that. It's not so clear why a logarithmic scaling should emerge, and it's interesting to try and understand this from a standpoint of quantum chaotic dynamics, because this really is happening under the action of this random circuit as a function of time. So it's directly tied to dynamics. And our main technical result in this paper up here is to tie the shadow norm, which is this quantity that controls the sample complexity of the protocol, to properties of operator evolution. And so let me give you the technical result here. We're going to use, first of all, general Q-state Q-level systems, so Q is of dimension Q. And when we say a Pauli operator, we mean a product of these clock and shift operators, which are unitary, though not Hermitian. So that's the generalization of Pauli that we're going to use. And we're going to take our third operator, O of t, again, t stands for the depth of the randomizing circuit, and we expand it out into Paulis. So P now runs over all possible products of x to the a, z to the b, over all qubits. And there are going to be some coefficients here that depend on time, on the depth of this circuit. From these coefficients, we can build a so-called weight distribution by adding together the absolute value squared of all the coefficients of Paulis that have the same weight, meaning they act non-trivially on the same number of sides w. And what we obtain is really a probability distribution in this, on the set of possible weights between 1 and n. So a single side Pauli all the way to a completely many-body Pauli. And this is, non-negative and normalized to 1 by definition. And you can see here that, essentially we start our twirling from a weight k Pauli. So this distribution is a delta function at the initial time. And then as time goes on, something happens to it, presumably broadens and moves. And then eventually, when we run an infinitely deep circuit, it becomes a completely random Pauli operator, which is going to be, essentially random on each site. So for example, on qubits where there are 4 options per site, identity x, y, and z, this is going to have an average density of Paulis of 3/4 of n. So each side has average weight 3/4, and you add them all up, and you get some kind of Gaussian distribution peaked around that value. So there is some dynamics in this weight distribution as a function of time. And what we find is that the shadow norm of our Pauli operator is given by this particular kind of convolution of functions of the weight, which you can interpret as the harmonic mean of the local twirling results that we saw earlier. So just to remind you, we saw that if you go in and you do only single site random rotations, then the scaling of shadow norm is as 3 to the k, where k is the weight now. So for general Q, this becomes Q plus 1 to the k, turns out. What we have here is essentially saying, do the following thing. Take this result, take its inverse, so we get Q plus 1 to the minus weight, take the average, and finally take the inverse again. So it's some kind of average of those local twirling results, but it's perhaps not the one might have expected. So this is just I'm not going to go into details on the calculation, but it's a thing one can do straightforwardly by using randomness of the gates at the start and the end of that circuit, particularly the two-design property. So yeah, we have to assume this local scrambling property in our ensemble of random matrices. Okay, so again, what do we do with this? We have found this relationship between the sample complexity of the protocol through this quantity called the shadow norm to the dynamics of operator weight under random circuit, which is expressed here. And again, this is a bit complicated, but in a nutshell, this is simply saying that the bigger the weight, the bigger the shadow norm. This is some kind of average of something that is blowing up exponentially with the weight. Okay, so I guess we have to explain why the weight goes down first and goes up later. And this is simply it's easy to see if you think about one of these initially completely packed pi operators, meaning that they are identity outside of some segment and they are traceless on each one of those points. So it's x, y, and z on each of them, or generalizations thereof for higher dimensional qubits. And as time goes on, two things happen. So first of all, the operator spreads. So at the boundary, we have a butterfly velocity emanating out, and we can have non-trivial pi operators where previously there weren't. This is just a statement that there is a propagation of information in a chaotic quantum system with some ballistic shape and some butterfly velocity. And this is going to increase the weight on average, because now we have more places where there can be non-trivial Paulis as a function of time. On the contrary, if you focus on the interior of this segment, as a function of time, you might have, instead of this completely packed configuration, you will find some holes. Some identities are going to pop up inside your operator. And this is, of course, going to drive the weight down on average. And so we start out from a density of 1, and at late times we converge, we're going to asymptote towards some final density that's at equilibrium for a random Pauli. So 3/4 for a qubit, generally 1 minus inverse q squared in higher dimension. So just saying that there are q squared Paulis, and one of them is identity, and this is a fraction of non-trivial Paulis you will get. So both of these things, both the spreading and the relaxation, really are captured by familiar quantities like the out-of-time ordered correlator, which of course has I suppose its most common usage is to diagnose the front of the information spreading, and that's what gives you the this butterfly velocity and describes the operator spreading part. But also, if you focus on the interior of this light cone, you will find some exponential convergence to some asymptotic value, and that is roughly what is describing this process of operator relaxation. Suitably averaged overall kind of local Pauli matrices you could be taking the OTOC with. Okay, so putting these two processes together, we can find a very simple heuristic picture for why this kind of behavior should arise. So essentially, the spreading is taking place from the boundary of our operator. So, of course, this is where new Paulis are being produced. On the contrary, relaxation is taking place anywhere inside the bulk. So wherever you are, there's now some probability of spawning an identity. And for a sufficiently big segment, for a sufficiently large K, the bulk process is going to win at the start. So if you roughly take a derivative of the weight, it's going down with a bulk term and up with a boundary term. It's going to become negative for a sufficiently big pi operator. And so this is what accounts for the fact that this quantity is initially dropping as a function of time. But then later on, at some point, we are sufficiently close to equilibrium. We've got about 3/4 or whatever the correct fraction is of non-trivial Paulis on its side. And our operator is going to continue growing ballistically with time. And this is what accounts for this exponential blow up with t. So there is going to be an optimal depth for this protocol at some value of t that kind of optimally balances these two processes. And this is what this picture is trying to show. And the next part of the talk, I'm going to go into a little bit of how we essentially solve this process of relaxation in one dimension and how we can derive the scaling of this optimal depth and the associated performance. Okay, so I'm going to focus on systems in one dimension where this is really solvable in a neat kind of simple way, though the kind of broad picture is also applicable to higher dimension. So what we do is we look at this problem of relaxation of Pauli density in a very long Pauli operator. So let us take an infinite Pauli operator that is a tensor product of traceless Paulis on an infinite chain. And we want to know what the Pauli density looks like at any one point of this infinite chain. Of course, this is translational invariant, so it doesn't matter, as a function of depth. And here we can leverage some earlier results by these papers that looked at operator spreading in random circuits. And it is known that we can, instead of looking directly at operators, we can just look at a classical probability distribution over some occupation configurations. So let us associate to each side binary variable that is 0 or 1, depending on whether the site stores an identity or a traceless Pauli. Okay, I'm going to use this open circle for the identity and this solid circle for a traceless Pauli. Any one of them, doesn't matter. We can, map any operator into a distribution over these occupation configurations by simply taking summing the squares of all the coefficients in a Pauli expansion that match this pattern. And it turns out, from, for example, these papers, that these probabilities evolve according to a Markov process over time. So each time step is some kind of transition matrix that hits this probability distribution. You can think of this as, in the real dynamics, there are coherences, there's interference at later times and so on, but we're doing an average over random gates at each time step. And this kind of washes out all such coherent effects, and we end up with this classical Markov process. So the building block of this for two sites being hit by some random unitary gate is this transition matrix, where you can see that the identity state is invariant, as it should be, just by conjugation by unitary, it leaves the identity invariant. And then any traceless Pauli has equal likelihood of ending up in any other traceless Pauli. And that gives you some fraction of kind of identity Pauli, some fraction of Pauli identity, and some fraction of Pauli, which are given by this number here, 1/5 for qubits, for instance. So again, the thing we want is getting this Pauli density as a function of time in one of these sites, but it's going to be convenient to look at the sort of complementary variable, the density of holes, as a function of time. So I'm just taking 1 minus n, and I get this kind of diagrammatic expression here where I have a fully packed initial state, I have a hole here, and I don't really care what's happening to the other sites. So I introduce this plus variable that is a sum of identity and Pauli, meaning that in this summation over here, I simply add up over all the states that are not at site I. And that's represented diagrammatically with this symbol.
Can I ask a question?
Sure.
So what you're showing is the Markov matrix for two sites.
Yes, how random
and we
two
have
sites.
to extrapolate that to a Markov matrix of n sites.
Yes.
So
tensor product over pairs of sites in a Brick structure.
Okay. So I'll ask a question at the end. Thanks.
Yeah, sure. Yeah, and please, everyone, feel free to interrupt. So this is the big many-body diagram we want to compute at the end of the day, and to do so, we note that this has a simple structure. Let me go back to it. If we start from the back and evolve backwards, so in the plus and identity variables, this has a neat structure that I discuss here. So in particular, imagine an infinite domain of identities that is, of course, invariant because of this column here. That's 1, 0, 0, 0. And physically, because the identity is an eigenmode of a unitary circuit. An all plus state is also invariant for a slightly different reason, which is just conservation of probability. It's saying that this is a stochastic matrix, and if you sum all the rows in this M transpose, you get 1 for each of them. So these two states are invariant. What happens is that if you now have a semi-infinite domain of identity touching a semi-infinite domain of pluses, then this domain wall between them evolves in a simple way that is going to describe a random walk. So you can see the calculation here. Maybe it's not so illuminating, but the important point is that this sort of domain wall between, imagine a semi-infinite domain of identities here and a semi-infinite domain of pluses over there, where they touch is going to hop either to the left or to the right with probability a n1 minus a. So again, 1/5 and 4/5 for qubits, for instance. So this describes a biased random walk of this domain wall. And the bias tends to expand the domain of identities. So we start out from this configuration where there are two domain walls that are neighboring to each other, and they will tend to walk outside, walk away from each other. But of course, they can fluctuate and annihilate each other if they touch. Like if they touch, if you have two of these domain walls next to each other, and both of them, have bad luck and produce ++, then the domain is gone, and you have an all plus state, which from this point forward propagates all the way back and contracts with this boundary and gives you 1. On the other hand, if the domain walls fail to annihilate, and if they make it all the way back to 0, then you're going to have a bunch of these inner products between empty and occupied states, which is like taking the trace of a traceless Pauli. So this is going to give you 0, and any diagram that looks like this is going to vanish. So we have reduced our problem essentially to the annihilation probability of two random walkers with a bias in some number of steps that's t or less. This is our density of holes that we're calculating with this diagram. And the thing we wanted was the complementary variable, density of particles, or 1 minus this density of holes, which from this we immediately see to be the survival probability of these two random walkers as a function of time. And this has, this is a well-known problem, that there's solutions that you can look at. And it turns out for our parameters that indeed we recover the expected asymptotic equilibrium density. This makes sense because the survival probability, these random walkers are biased outside. So if they make it far enough from each other, they're essentially safe. They will never annihilate. And so there is some asymptotic finite value that reproduces the expected Pauli density in a random Pauli. But then there is some leading sort of asymptotic approach to this, which has an exponential piece with this rate gamma and a universal power law correction that comes from this first return probability of a random walker, t to the 3/2, to minus 3/2. The rate gamma, I'm not going to say much about it, but essentially for experts on random circuits, this happens to be the entanglement velocity. So that even though I'm doing everything in an operator picture, there is also an entanglement picture that can be applied here. Okay, so this is all I wanted to say about this solution, but essentially we can now take this and use it for understanding the behavior of this protocol, of this shadow norm that describes the sample complexity. And to do something easy first, we can use an upper bound, right? So by convexity, we know that we have an exponential, and we can bring the average into the exponent at the expense of introducing an inequality here. And by doing this here, by bringing the average into the exponent, we find that our shadow norm is exactly bounded above by this power, or by this exponential of the average weight, shown here. But now this quantity is pretty simple to compute because it's just the average size of our Pauli, which is the initial one plus 2 VBT. 2 comes from the two edges, of course, and VB is the butterfly velocity that describes the slope of this light cone. And then, being a bit simplistic, on each side inside the support, you can attach the average density we found for the bulk. Of course, near the boundary, there's going to be some modulation. This is going to go to 0 smoothly with some kind of like error function behavior, but it doesn't really matter. To reading order, it's okay to associate the bulk density to each one of these sites. And if we do this, and we use the solution we found, we obtain the tightest upper bound at a time, at a depth, which scales in this way. So it has this 1/gamma, that's the rate. It has a leading logarithmic in K behavior, like the kind of numerical observation that we were trying to explain. But then strikingly, it also has this subleading correction that is a double log with a universal coefficient of 3/2 that comes exactly from here. It's a reflection of this random walk behavior that we found. And now we can plug in this optimal depth into our upper bound, and we find essentially this kind of scaling with, for qubits, for instance, it's 3 to the 3/4 to the power of k, which happens to be about 2.3. So, numbers don't matter so much, but it is an exponential gain over the 0 depth protocol that was just, individually randomizing the qubits. Here, by doing this kind of many-body process for a logarithmic depth, we bring this down substantially to some lower value. However, this bound we use is not at all tight. It's exact, but it's not tight. And we can do a bit better, not exactly, because this is after all, it's even though it's kind of a Markov chain, perhaps in this random circuit model, it is somewhat complicated. But we can, in an approximate sense, by neglecting correlations between Pauli density at different sites and using some kind of mean field approximation, we can find an estimate of the true behavior. And surprisingly, it happens to have the same scaling of optimal depth, even though it's very different, numerically. The value is different, but the optimal depth is the same. The optimal scaling of sample complexity happens to be about 2 to the k for qubits, so 2 to the k in general, which is near optimal for reasons that go back to the global twirling that I briefly flashed earlier, where if you do a global random Clifford, the sample complexity scales as 2 to the n. And that is about the best you can do if you are allowed to completely randomize some set of qubits. Here, the best thing you could do with prior knowledge of I want operators on this particular segment, you could go in and do a global Clifford on that particular segment, and this will give you 2 to the k. So in this sense, this is near optimal. This is why we put this lower bound here, and this is essentially touching it. So remarkably good performance given the constraints. And then just briefly, I'm gonna go over some numerics we did to confirm this picture. And we used infinite matrix product states to simulate directly the Markov process in the identity and Pauli basis. And this process isn't very entangling. So for a modest bond dimension that you can probably run on your laptop, you can get very good data on infinite systems and extremely big Pauli operators on them. We got up to 1,000 sites. And beyond that, really the limitation is kind of machine precision. At some point, you get kind of astronomically big numbers, and the computer complains. But essentially, we can see here data points from these numerics compared to the solid line is our mean field prediction. And as you can see, there are some deviations, particularly at early time, where correlations are presumably significant. But then at late times, this is essentially exact. It means that correlations have died out and mean field becomes nearly exact. I'm also highlighting with circles the position of the optimal depth. And as you can see, it's roughly logarithmic, but let's say, this curve here is roughly exponential. It's so that the granularity is such that this is pretty hard to fit to any curve, right? We would really like to get better data. And we do that by employing a trick that we call gate dilution, which simply means in your ensemble of random circuits, in addition to picking a random measure over hard random gates, you can also pick randomly whether a gate does or doesn't happen, right? So you can set this value epsilon to be, if it's 1, then always do a hard random gate. If it's less than 1, then skip it with that probability. So for example, for 0.5, you'll get a more sparse sequence of gates. And this allows you to kind of go through these dynamics in slow motion in a sense. So, over here in the undiluted case, there's stuff that's happening very fast in between, data points that are these discrete time steps. And by diluting the gates, we can slow it down so that it's almost continuous, like almost nothing is happening in between time steps. And so instead of having all the action happening over here, we can stretch it out and get a very good resolution on the temporal behavior. And it just turns out that if we rescale time appropriately by this rate gamma that I mentioned earlier that describes the relaxation process, then all of these curves collapse fairly accurately, which is to say that there is some underlying continuous time dependence. And by doing this kind of discrete time process, we are sampling it at different intervals. But ultimately, there is some underlying roughly continuous in T behavior. And so finally, we can use this trick of dilution to slow things down such that instead of having all of these steps, we have a really kind of smooth and continuous behavior. And by using our MPS method, we can get up to 1,000 sites and get very good evidence that the scaling with K is in the form we predicted. So there's a leading log and there is a minus 1.5 roughly log-log correction, which is really non-trivial and also shows up if you look at kind of discrete derivatives as shown here. So again, I want to emphasize that this prediction is kind of rigid. These 3 halves really comes from the random walk picture. It's not tunable, and so it's remarkable that it comes out of this numerics. And finally, you may see that the kind of upwards concavity that this induces is, probably responsible for this observation of a log squared behavior here, which is probably an artifact of this. And the leading behavior is in fact logarithmic. Great. So I think I'm pushing it close to an hour. So I'm probably just gonna stop here. I wanted to, briefly mention some recent works that I've been interested in bringing these kinds of randomized protocols to analog simulators. But I know that you've heard about this from Max McGinley a few months back at, in the seminar series. I'm not gonna talk about it other than saying that, this is interesting and you should check out our papers on this. But let me just skip. And to conclude, I've given an introduction to classical shadows as a method for, learning many things about quantum states, measure first and ask questions later. I've then introduced recent variations on this, which go by shallow shadows, which explicitly involve kind of finite time dynamics in the randomization process. And I've shown how this ties to the competition of 2 processes in chaotic dynamics, operator spreading, and this other process of relaxation, and how this lets us get this optimal scaling of depth as leading log with this universal subleading piece, and how the sample complexity that we get is near optimal. So for the future, it would be interesting indeed to bring this kind of approach to within reach of analog simulators by exploiting this idea of deep thermalization that that I didn't get to tell you about. And also, this is, as I argued earlier, this kind of protocols bring together a range of ideas that are interesting in dynamics, so random unitary evolution, measurements, statistics of moments, and so on. We have seen here how this gives one particular connection to one topic in dynamics, but I'm fairly sure that there are other interesting things one could do, particularly bringing in monitor dynamics, which is another topic that I've been interested in recently. So let me thank you one more time for having me. Thank you for your attention, and also thanks to my co-authors Yadong, Tibor, and Vedika, and also to Wenwei Ho, who's my collaborator on some of the works on deep optimization that have largely motivated my interest in this kind of thing. So I'm happy to take any questions. Please just unmute yourself and feel free to ask.
Great, thanks a lot. And I guess Juan can ask the question now.
Hi, thanks. It's more of a comment. Can we go back to the classical model?
Sure.
So, yeah. So I know that you do the circuits, so you put all the even gates and all the odd gates.
Yeah.
But that's what's called the Fredrickson-Anderson kinetically constrained model. Yeah.
Mm-hmm.
So it's been known for a while.
Mm-hmm.
So I'm guessing that several of these results are equivalent to results that exist for that model already. Just the classical. This is the classical model for spreading. So now, and some things are known, and some things are known not in this context of the circuit, of the like brickwork circuit, but in the context of lattice evolving either with Monte Carlo, the discrete or continuous Markov dynamic, continuous time Markov dynamics. And some results are known rigorously, like why you have a ballistic front, the speed of the ballistic front, the fact, what's a rigorous result is the fact that once the front passes, the thing that left behind equilibrates in the classical stochastic sense. Mm-hmm. So that's not, that's well understood. So that's the comment I wanted to make. I think there are direct connections, and maybe some of the results you have already exist in some disguise, and maybe there are existing classical results that might be useful. Certainly,
that's a great point. Thank you. And in fact, part of this, I would say, the only novelty of what we did really was kind of mapping this to something easy that's well understood. Of course, for example, the scaling of this quantity here for random walk was super well known. And also, the classical equilibration in these Markov processes is also, as you said, being well studied. I didn't specifically find this question addressed, but I guess that yeah, I'm not an expert on that field. So actually, if you have references on this, it would be also interesting to look at.
Yeah, I can send you an email, an explicative email. Yeah, thanks.
Okay, any other questions? Okay, since we're right on time, I guess I can stop the recording.
Okay, thanks.
Just